All right, so ozone. Ozone is formed in the upper atmosphere in the stratosphere. So it's above the troposphere. It's one of the few things that actually happens that makes a difference to us outside of the troposphere. As you remember, we talked about the layers of the atmosphere, and about 95% of all the gas in the atmosphere is in the troposphere. The effects, by the way, of global warming are in the troposphere. That's where it primarily happens. Weather all happens in the troposphere. So the stratosphere's only claim to fame in this case is the fact that the ozone layer forms here. And you have a reaction. You have the normal stable form of oxygen gas, O2. They like to pair up, share their outer electrons. You probably, hopefully remember from chemistry that many of these molecules are diatomic. And it's a stable form for them. But in the upper atmosphere, ultraviolet radiation has the property that it likes to break chemical bonds. Okay, it's what they call oxidizing radiation. It's one of the reasons why we don't want it down here at our level. But up there, where it's unshielded, it will cause these pairs of molecules to briefly break apart. Now, a lot of them are going to go back to O2. That's the way they're most happy. But some of them will regroup together as O3 temporarily. And in so doing, they're going to absorb a lot of that ultraviolet radiation. And then another property of it is the fact that O3 molecules, ozone molecules, absorb ultraviolet radiation before re-emitting it, and therefore take the energy off of it and reduce the length of the wavelength, make it less energy, and less with the actual ultraviolet wavelengths will make it to the Earth. About 95% are blocked out by this process. So that's a good thing, of course. That's the natural way of things. So we always look at the way the nature is and everything and the function it serves life, and that's obvious that's filtering out that UV radiation is a very good thing for life here on Earth, life on the surface of the Earth, of course. So how do we mess this up? Bullet 4. Humans have produced these substances called chlorofluorocarbons, and we'll talk a little bit on the next slide about why we did and use such things. But suffice it to say, it is a completely artificial molecule. You do not find this in nature in any great quantities, or there's no process that naturally makes this happen. Most of your chlorine and fluorine are already bound up with metals. So it's not something that would normally happen. It was manufactured starting in the 1930s, and it serves a lot of purposes, as it is. But one of the things that it does is that when these substances get into the upper atmosphere, that same UV radiation that catalyzes this reaction now will act upon this chlorofluorocarbon, that chlorine stands for chlorine, and break one of those chlorine atoms off. Okay? And there are a few things more radical than a single chlorine atom. So that chlorine atom is going to immediately go and grab onto an oxygen atom and break off one of those oxygens, and an ozone molecule, and break off one of those oxygens to form ClO, chlorine oxide. And from there, that particular molecule is also pretty reactive. Not as much as the chlorine atom, but it's a reactive molecule. This is what you have actually when you dissolve bleach and chlorine and water to make bleach. So that chloroxide atom or molecule will go on and react with the free oxygen atom from these processes above and form your O2 molecule there. It's stable. That's part of what drives it, is that formation. And that then, of course, will release that chlorine atom. Okay? And that chlorine atom then can go right back here to where it started, and the whole, oh, there it is, right there. The whole thing can get started again. All right. So you guys got that all memorized, right? Very simple process, no big deal. Just boom, boom, boom. That's it. No big deal. Now it's a lot, so I want you to understand the most important things to know about this. Okay. First of all, what a CFC is, the elements that are on that CFC molecule, carbon, fluorine, and chlorine. And most importantly, that chlorine atom that's on there is broken off by UV radiation. And then that chlorine atom can go through and disrupt the formation of ozone. And it can continue to do that through a series of processes. It gets recycled, it becomes a free chlorine atom again, and can continue to break down ozone after ozone after ozone molecule. The estimate has been that one CFC molecule can break down about 100,000 ozone molecules. Okay, so that's a big part of the problem. You don't have to put a whole lot of this in the atmosphere to make a big difference. All right, so that's the reaction there. That's how people mess things up. Took us a little while to figure out this would happen. One of the things was that the people have known about this ozone shielding for over a century, and there's ways of telling how much of that ozone is in the upper atmosphere through satellite imagery and stuff, and also other observations from the ground, because we've got data going back before the 1950s, and what we've seen that it has decreased. They started noticing that it was decreasing, and it got to the point in around 2000 where it was about 50% of what it was in the 1950s. So that's a radical reduction. Okay. So we'll look at the next stage about what we did about that. So that's a call to a wake-up call, so to speak. This does occur, by the way, in the stratosphere, as mentioned, so we can get rid of this answer here. Otherwise, the other things that are in there are correct, except that's not how you spell fluoro. Thank you. Eraser. Fluorocarbon, F-L-U-R. Fluorocarbon. Okay. Fluorocarbon.
Oh my
You
God.
get the picture, okay? You can look it up if you want to have the correct spelling, but anyway, so that's where this ozone depletion occurs. The stratosphere is where it is, and the layers in that have decreased. One of the things you'll hear a lot about, and they ask about it on the national exam, so we should give it due consideration, is the ozone hole. The ozone hole is simply actually what happens naturally with the ozone layer over the poles, and what the effects of these CFCs have had on, to the point where the ozone naturally thins out around the polar regions, particularly the South Pole, because of polar vortexes and wind patterns and stuff like that. And then when you combine that with the CFCs, the action of these CFCs and other ozone-depleting chemicals, then you end up where they've actually documented a hole, a complete window through that layer of the ozone layer, so that 100% UV radiation can get through. That may seem a little frightening, and it would be if it were any place other than the South Pole. So at the South Pole, fortunately, that's where it's occurring. I'm not sure exactly why it doesn't occur at the North Pole. Maybe Santa has an ozone generator he keeps cranked up so he can continue to work all year round. But at the South Pole is where they have documented and noticed it. And fortunately, of course, at the poles, you're not getting the energy from the sun is at its least, because it's going basically directly over it. The angle of incidence, as they call it, is very great. So it's not hitting right off like a perpendicular like it is at the equator. Second thing is, there's not a whole lot living down there, particularly that time of year. About the only thing that it really directly at the South Pole lives is there's a period where the penguins are there with their eggs, but that's during the winter, and this is actually their spring right here. This is our fall, early fall or late summer, early fall, and their spring, early summer down there. So that is over Antarctica. Put that in there. And that is what's known as the ozone hole. The reason why I kind of dismiss this a little bit is because, like I said, in that position and everything, it does have a huge effect on that. And I think it's kind of for sensationalism that people say, there's a hole in the ozone layer, watch out. Well, if that hole was actually over, like a city or something, or over the equator for sure, you would see extensive damage to crops. I would assume that you would go outside and literally start to bake within minutes if there was an actual because it normally blocks about 95% UV radiation. So it would be pretty nasty at those latitudes. Any questions? No? Alrighty.